Hello, everybody, and welcome so much to Pint of Science 2021. My name is Josh Rasera, and I am a third-year PhD student at Imperial College London, and I have the honor of being your host tonight for this Atoms to Galaxies broadcast. Thanks so much for joining me. Before we start, I just wanted to remind you that this is very much an interactive event, so any questions or comments that you may have for any of our speakers, please do post them in the chat, as we're going to be having a live Q&A in the second half of our show, where they will be answered by our panel of experts. Also, if you're a Twitter user, please do feel free to tweet at us. Our handle is @pintofscience, and please use the hashtag Pint21. So our focus for the next hour is on the future of space exploration. Specifically, we're going to talk a lot about space resources and how they're going to fuel our journey to the moon, Mars, and beyond. Usually, the first and most basic question people have that they ask me when I talk to them about space resources is, why do we need resources in space? What are they good for? Well, over the past few years, there have been several splashy articles in the news about how we could mine trillions of dollars worth of platinum from an asteroid or something like that. And while this, sounds great on paper, the practicalities of doing something like this really, aren't there. Furthermore, mining platinum from asteroids doesn't really help us with space exploration in any way, shape, or form. Instead, what we're going to focus on talking about tonight is something that's far more useful than space gold: fuel. As an example, I want you to think that, or consider going on a very, very long road trip, pretty much all the way around the world. You've packed your car, you've got your favorite snacks and drinks, you have your map or your GPS, and your fuel tank is full and you're ready to start driving. So you begin. How far do you get before you're running on fumes? Will you be able to make it the whole way around the planet before you need to refuel? How can you possibly ensure that you have enough fuel to finish your journey? Well, you could rely on petrol stations. This is a possibility, but they're few and far between in some spaces on the Earth, and that might not be the most reliable thing to base your journey off of. You could also bring fuel with you. Again, possibly, but this might not be the most practical. I mean, you're going all the way around the world. You're probably going to need a tanker truck full of fuel in order to keep yourself, going the entire way around. And on top of that, you're going to totally kill your fuel economy by bringing so much extra fuel with you. So it's not really the most useful or practical way of going about doing this. But what if you could bring along some sort of magical device that could just take raw materials that you find at the side of the road and convert it into gasoline or diesel for your car? That would definitely be the most preferable. Now, I realize this analogy is a bit of a stretch, but it does do a decent job of highlighting some of the challenges that we face with deep space exploration. There are no service stations in space to refuel our rockets or our satellites. And while we can build bigger rockets with more fuel capacity, it really can only get us so far. Earth has quite a strong gravitational pull, and so if we want to launch a bigger and heavier rocket, we need to have more fuel in order to get it off of the surface of the Earth. But as we add more fuel to the rocket, that adds weight to the rocket, which begets the need for more fuel in order to launch that fuel off of the Earth, and so on and so forth. And you can see that very quickly, this starts to be sort of a limiting returns kind of situation. So really, at the end of the day, our only option is to make our fuel in space. And we can do this from water or other oxygen-bearing minerals. Fortunately, today, I'm joined by 3 space resources experts who are going to guide you through the process of making fuel in space. Everything that you see and hear in the next hour or so is not science fiction. It is real, active research that I strongly believe that you will see on the moon in the next decade. So I hope that you're all excited for the next hour. I sure am. And in order to get things rolling, I'd like to invite my first speaker, my friend, Dr. Abigail Calzada. Abby holds a PhD in geology from Birkbeck College at the University of London and is the lunar exploration expert at iSpace Europe SA in Luxembourg. Today, Abby will be talking about water, a key resource for producing rocket propellant on our closest celestial neighbor, the moon. Welcome, Abby.
Hello, good evening, good night, everybody. First of all, I would like to thank Joss and Pint of Science for allowing me to be here with all of you to talk about one of my favorite topics, lunar resources and lunar water. So I would like to start with this exercise. It's like I just choose one random image from Google Images, I put lunar base and I choose a random image. And this one, for example, we see several systems that we can see here. We see some solar panels, we see some kind of greenhouse in the middle, we see some habitats that are being covered by regolith. So it's like what type of resources we need to use to build and to maintain this habitat. And something else is like, what of these resources can we find on the lunar surface? Or in this topic, we are going to focus in lunar water. So I want you to think, it's like, for what we will need lunar water or hydrogen and oxygen in this type of base. And you can do this exercise just choosing another type of image from Google Images. It's like, okay, I have lunar water, I have hydrogen, oxygen, why we can use it. For example, I'm going to start. We can use it we have these astronauts here. And obviously, if we have astronauts, we need to have some water for drink, some oxygen for them to breathe, so that is to keep them alive. And also, I assume that these astronauts will want to go back to the Earth eventually. So they will probably go back to their homes in a rocket that is filled with lunar water, hydrogen, and oxygen as a propellant. So it's like, until quite recently, it was considered that the moon was a really, really dry body. And it's quite like that. It's pretty dry if we compare it to the Earth. However, in the last missions, like around 10 years ago or something like that, there were missions who detect water ice in some locations on the moon. But not just that. It's like there are some researchers that they found in the Apollo samples, they found minerals that also contains tiny amounts of water within this mineral, within the structure. So it's like, wow, actually there are some water and water ice on the lunar surface. That's great, but where did this water come from? So here I divide it in two parts. First, the water that is in the moon from the very, very early stage, what I call the primordial moon, and then the water that is still being received by the moon even nowadays. So what I say primordial moon, what I mean? What I mean is the moon at a very early stage, around 4.2 billion years ago, where the moon was just a big ball of molten rock. So at that time, also in the inner solar system, there were a lot of bodies, a lot of comets and asteroids going around. It was quite busy place. So this primordial moon was being bombarded all the time with these materials. Comets, they have a huge amount of water. Actually, a big part of the composition is water ice. But also asteroids contain some water. Here in this image, there are two different types of asteroids. The one that is 10 to 20% is like chondrites, that type of asteroid. But then there is also carbonaceous asteroids, that is other type, that they have also small amount of water, but they still have. And also during the process of the formation of the moon, there were water already in the materials within the moon, but really tiny amounts. Here it says between the 10 to 300 parts per million of water. How we know that? How we know that these were the primordial sources of this water on the moon? It's like, as I mentioned, there are some researchers that they took some Apollo samples, they did research and they found this water ice within these minerals. And these minerals were formed during this stage. And actually we know what portion came from comets, what portion came from asteroids, and what portion is from the moon itself, because we can analyze the isotopic signature of this water. However, right now, even although there is not so many bodies bombarded the lunar surface, the moon is still receiving some water input. Still, from time to time, there are comets and asteroids that are hitting the lunar surface, providing some small amounts of water, some part of water. We have the interstellar dust particles, IDPs, that also, they are bombarded continuously on the lunar surface, that also bring some water. The giant molecular clouds, they bring very, very tiny, almost practically negligible. And also the solar wind carries some volatiles like helium and especially hydrogen. So when this solar wind impacts on the lunar surface, this hydrogen gets implanted in the lunar soil. It interacts with the oxygen that is in the minerals there, and it can found bonds and found molecules, water molecules or other type of molecules. And as I mentioned, there are the moon, that the primordial water that were already contained on the moon. So okay, we have this water thing arriving on the lunar surface, and it start travels, because in the lunar surface the conditions, the temperatures and the pressure are not stable for these molecules. So usually they tend to escape to the space. but particles of them can be traveling through the surface, like doing little bounces, and until they find a place that are more stable. Sometimes it happens that there is an impact nearby, and there is a lot of lunar soil that is ejected from this impact and covering this lunar water. Or also it happens that this lunar water can react with the minerals and form some kind of bonds that we don't understand very well yet. But eventually they could travel, and some of this water can reach locations that are they are cold enough, that they are dark enough, that the water remains stable there on the surface. And actually, those areas are specifically located in the poles, in the North Poles, like we see in the A image, and the South Pole in the B images. And this water ice in the surface was detected by some instruments, mainly in two missions. One is in the Chandrayaan mission from India, especially by the M-Cube instrument, that is an hyperspectral imager instrument, and also by several instruments by the Lunar Reconnaissance Orbiter. That it is a mission by NASA that is still around the moon. So what we see here is like these ice exposures are specifically located in the interior of the craters, and that is for a reason. It's like the bottom of these craters, because the solar inclination of these areas and the topography, sometimes they never receive solar illumination. So that makes the areas really, really cold. And when I say cold, I'm talking about minus 200 degrees Celsius at least. So really extremely cold. But what happened here? That we have no idea how this water ice is. It can be water ice mixed with some lunar soil, or it can be the other way. It can be some lunar soil mixed with some water ice. We don't know how deep this water ice can go. We don't know anything about it. We don't know if actually it's water ice or if it's other type of bonding. We have a lot of uncertainties. And going there and explore these deposits is not easy neither, because these areas are very delicate areas. So if we go there, we can disturb, and all the information that this deposit has, or all this deposit can simply disappear. Fortunately, we have another option. There is the lunar regolith, or the lunar soil. This lunar soil covers the entire moon. And as we see here in this, well, it's formed by dust particles, by other particles more like sand, rocks, even boulders. We have an image here with these nice footprints from the Apollo astronauts. And as we see in this diagram, at least 42% of this material is formed by oxygen. The problem is, like, this oxygen is not a gas like we have it here in the atmosphere. This oxygen is bound to minerals. So we need a way to extract this oxygen and to use it. I think I'm going to stop it here because my colleagues Reuben and Bethany are going to go deep into how to extract this oxygen. I hope that you have many questions, and see you later during the question round. Thank you very much.
Thank you so much for that, Abby. That was so interesting. Hopefully we'll start seeing some questions come in through the chat and the Q&A. This is just another reminder. Please post any questions that you may have. Again, we will go through them all when we get to the end or the latter half of the show. Thank you again, Abby. That was really, really so interesting. So Abby's given us a great introduction to water resources and the ones that are specifically available on the moon. But a question that many of you may still have is, how do we actually get our hands on these resources? How do we get them out of the Earth, or out of the moon, I guess? Well, our next speaker will help to shed some light on this problem. I am now joined by Reuben Cruise, a fellow PhD student of mine at Imperial College. Our research group specializes in dry mineral processing technologies, and Reuben is our expert in electrostatic charging of materials. Today, Reuben is going to be diving into some of the specific challenges, I should say, associated with mining on the moon. Welcome, Reuben.
Thanks, Josh. It's great to be here and to share a pint with you all. I was hoping to bring a Guinness, but it's a bit too rainy to go out and get it, mainly because it's black like space. But this is it's a home brew from a member of our group, Lucho. So if you're here, Lucho, cheers. But yeah, I suppose I should talk about some science as well. So here to talk about differences between the moon and the Earth, and basically challenges for getting oxygen out of the moon dust. So the latter stage of Abby's talk, where she talked about oxygen. So oxygen on the moon. As Abby mentioned, the moon is greater than 40% oxygen, the regolith, or the dust. It's not great for growing potatoes out of, but you can get really useful stuff out of oxygen. But how do we get it, is the question. Basically, you have to dig it. After you do that, you might need to separate out oxygen-bearing minerals, and then you need to extract the oxygen from these minerals. So we'll kind of go into this in a little bit more depth through the talk. But first, a little bit kind of food for thought. I thought maybe if you had any ideas for kind of ways the Earth and the Moon are different, maybe you could pop them in the chat. And kind of how might these differences between the Earth and the Moon kind of lead to problems, or maybe even benefits for exploration, not necessarily just for resources. Maybe we can have a talk about them towards the end. But I'll get straight into some differences, not an extensive list. But first, the Moon has about 6 times less gravity than Earth. The Moon is a lot smaller, and so there's a smaller gravitational pull. And so a lot of things are different, and you'll find that it might be easier to jump higher, but getting around, walking will be more difficult. And also, we'll find that this actually has difficulties for kind of mining processes. Another difference is that there's no air on the Moon. It's a vacuum, which also means that there's no liquid water. So there's really not a good supply of liquid water, and it doesn't stay in the vacuum. Furthermore, there's a lot of static charge. So if you see this picture of the astronaut, he has a lot of dust sticking to him. And this is actually very similar to, like, if you get a cat and drop it in a box of styrofoam, you're going to get the thing sticking to it. So that's kind of a result. And the lack of an atmosphere really adds to the buildup of static charge on the dust on the Moon. But so getting on from this and back into actual processing and actually getting oxygen from the regolith. So you have to dig it, gravity. So you weigh 6 times less on the Moon. And so imagine this, if at least when I was small and I was trying to dig in the garden, trying to dig into hard soil, I couldn't get anything in. I had to keep jumping on the shovel. And the same thing is going to happen if I go to the Moon. I'm 6 times smaller, and basically it's going to be really hard to actually push down into the ground. So you're going to need to be, if you're digging down, if you need to dig down, you need to be anchored. Or as Beth might talk about a bit later, if your extraction methods are efficient enough that you don't need too much regolith, you might be able to get by scraping the top surface instead of actually digging down. So you need less energy, and you actually won't need to put so much vertical energy in. We can move on to extracting. So this is something that Beth will talk about later, so I'm not going to go into too much detail. But basically, typical methods require you to heat the regolith up to really high temperatures, around 700 to 1600 degrees Celsius. For reference, this is similar to what you need for lava. So really hot temperatures, and this takes a lot of energy to do. So anything you can do to reduce the amount of regolith you need to heat up will save you energy and basically make it easier to do. So what you can do is basically reduce waste, reduce kind of particles in the regolith that you don't need. So things that don't have oxygen in them. And also some of these methods will need an optimal particle size. For example, they might not work well with really tiny dust particles or with, of course, larger rocks. So as an example here, if you have, say, imagine this is moon dust, and you have orange particles that are kind of, they're useless. There's no oxygen in there. They're just rocks. And then you have green things, they're oxygen-bearing minerals. And if you can just separate out the waste so that at least you have a better mix, you find you only have to heat up half the amount of regolith, but you get the same amount of oxygen out. So that's kind of the idea there. So yeah, so more oxygen per unit waste. So moving on to how do we actually separate? So first thing I mentioned was size. So on Earth, typically hydrocyclones are used for separating out small particle sizes. But as I mentioned earlier, there's there's not really any liquid water on the moon, and any water that is there is going to be really valuable. So you don't want to be using that for separation. And again, you might think about sieving, but this is really not very good for small particle sizes. So we've been thinking about kind of different ideas for how can we get around separating sizes. And one thing I like to think of is, I'm not sure how many of you had Lego when you were younger, but I used to have a big box of just random pieces. And I remember trying to get to small pieces. I always had to dig down to the very bottom. They're all stuck at the bottom. So what we've been looking a bit as this kind of vibrating. So this is one of our master's students playing around with vibrations, and there's larger particles and smaller particles. The purple particles are smaller. And vibrating for a minute or two, you find that the larger particles all come up towards the top, and we get a really good separation. So the thinking is perhaps we can use this instead of, say, water-based methods to separate by size. Moving on from sizing, we might need to enrich. So basically get rid of as much of the waste dust as we can and just have the oxygen-bearing minerals. On Earth, the main method used for this is froth flotation. So you basically put your dirt into a tub and you throw in a load of bubbles, and the minerals you want will attach to these bubbles and float to the top. But once again, as we mentioned, that there's really no running water on the moon, so this is not a very, very good option. So one thing that we are trying to look at is electrostatics instead. So for those of you who don't know, materials can have electrostatic charge, and there's two types of charge. So the first is positive charge, and if you have two positive charges close to each other, they will want to repel from each other. As you can guess, the other type of charge is negative charge, and of course two negatives will also want to repel. And then if you have a negative and a positive, they'll attract. So that's kind of a crash course into electrostatics and forces. So same charges will repel and opposites attract. And so if you get two particles and perhaps they're not charged, and you start hitting them together, they're going to start transferring charge between each other, so that you end up with like one with a positive, one with a negative, so they're different. And this is the same as the process when you, say, have a balloon and you rub it on your head and you're creating static charge that way. So our thinking is, can we apply this to mineral separation on the moon? So imagine you have a pile of moon dust, and you know that some of the particles are oxygen-bearing minerals. And can you rub them together, or can you shake them up in a certain material in a certain way such that the waste particles will gain, say, positive charges, and the oxygen-bearing minerals will more gain negative charges? Then you can put all this dust between, say, two walls, and you apply really strong charge to each of these walls, and you can try and separate out minerals this way. So basically a dry method, and you don't need any water. In fact, it's easier to build up electrostatic charges in the lunar vacuum, so this works even better. So that's kind of an overview of kind of how we can maybe use electrostatics for enrichment. So kind of a recap of what we've been talking about. The Earth is not the same as the moon. They're different, and differences in the environment mean technologies that you might use on the Earth are not necessarily very feasible on the moon. For digging, you need to dig. You can try and account for low gravity by anchoring into the ground or scraping. Not extensive, but these are two possible methods. For separating, for enrichment for size, you can potentially use vibrations or electrostatics to deal with this lack of liquid water. Yeah, so that's my little nugget of science for you. Thanks for listening.
Thanks so much for that, Reuben. That was great. Definitely some really interesting points to think about. And there's actually some questions coming into the comments now, which is even better. So we definitely look forward to talking more about size separations and separations by type in the latter half of the program as well. Again, just another reminder, please post your questions and comments in the chat. The more we have to talk about, the better. So thanks for that, Reuben. We'll see you again soon. Reuben's given us a great introduction to how we can get our hands on some of these useful minerals in space. Excuse me. But there is one critical piece of the puzzle left. How do we actually go from rocks to rocket fuel? To answer this, I'm now joined by Beth Lomax. Beth is a PhD student at the University of Glasgow and is currently working at the European Space Agency in the Netherlands. Beth is an expert in producing oxygen from rocks and will be telling us all about how it's done. Welcome, Beth.
Thanks, Josh, and thanks for having me. So I'm in my final year of my PhD with the University of Glasgow and the European Space Agency. And today I'm going to tell you about how we go from rocks to something that can actually fuel rockets. So to kind of go back over quickly, why do we need oxygen? This was already talked about by Josh earlier, but so firstly, to use as fuel at the lunar surface, and secondly, to use for life support at the lunar surface. And so in these cases, it's quite an obvious gain. Like any kg of material that we can use at the lunar surface is a kg of material we don't have to bring with us. And the third one is actually to refuel satellites. Any satellite in cislunar space, so anything orbiting the Earth, it's actually more energy efficient to take a kg of material from the moon than it is from Earth because of that deep gravity well. And then finally, to use the lunar surface like a pit stop for deep space exploration, because again, we can save a massive amount of launch mass if we can refuel as we go. And so you've already heard that the lunar regolith, or the moon dust, is actually 40 to 45% weight oxygen. But how do we get this out? Because it's tightly bound within the mineral lattices. So the process that we're talking about here is reduction. So reduction is just we're changing the oxidation state of the metal and we're extracting the oxygen out. And there's two methods that we can use for this. There's chemical reduction, where a chemical such as in this diagram, hydrogen, is used to pull the oxygen out of the mineral lattice, or electrochemical reduction. And in this case, we use passing current to kind of kick the oxygen out. And so I'm going to really briefly run through four of the most common methods. These have been investigated for many years and at different, some are at different maturities as technology. So the first one, hydrogen reduction, it's probably the most well-researched and the simplest reduction method. And it's around 900 degrees, but if you just put in plain regolith, the yield is only going to be around 1 to 3%. And so in this, the hydrogen's just passed through solid regolith in a fluidized bed reactor. It generates water, which can then be split into oxygen and hydrogen. And if you don't do any beneficiation, which is just a word for taking out specific minerals, if you don't enrich the soil first, then it's going to be a very low yielding process. The second method is carbothermal reduction. So in this case, we're using carbon or methane as the reducing agent. And this can be between 900 and 1,600 degrees. At the hotter end, you can get around 3 to 10% yield out, but it's a bit more, it's obviously hotter and it's more complex to handle molten regolith. And then what is generated from that is carbon monoxide and hydrogen, and the carbon monoxide can then be reacted again to regenerate the methane and then create water, which can be split into oxygen and hydrogen. And so both of those two methods have been investigated by NASA quite a lot in the last 20 years. They built full-size kind of pilot plant demonstrators that they then took out to the desert and tested, and that's where these yield values are from. And the third one, which is also being investigated by NASA, and a demonstration is actually being sent by the Israeli Space Agency, a company, to demonstrate this process, which is called molten regolith electrolysis. And this is essentially just electrolyzing lava. So the regolith has to be completely molten, so it's very hot. It has to be above 1,600 degrees Celsius. And the reported yields for this process is around 15 to 20 weight%. And this can generate metals and metal alloys directly, and then using an inert anode, which just means something that doesn't react with the oxygen, you can get oxygen out of this process directly. And then finally, molten salt electrolysis. So this is what I'm doing my PhD on. And so this process is being investigated a lot by the European Space Agency. And this brings the temperature back down to around 900 degrees. So the regolith, or the moon rocks, goes in solid and stays solid throughout the entire process. And the electrolyte, the liquid part, is actually a salt, and that's why it can be a bit lower in temperature. And then by passing current through the solid regolith, the oxygen migrates through the electrolyte and then collects at the anode. And so again, using this process, if you have an electrode that it doesn't react with the oxygen, you can make oxygen directly for use, which just requires filtering and cleaning. And so that's just like a bit of a visual picture of what the material looks like before and after. So on the left is simulated lunar dust, and on the right is what the material looks like when we've extracted essentially all of the metal. Sorry, all of the oxygen. So it's just a pile of metal left, and then hopefully that could actually find use with additive manufacturing as well. And so then, talking about lunar resources, I wanted to kind of pivot to Mars as well, because it's even more important to generate the resources when you're there, because it's just so far away and so inaccessible for resupply from Earth. And so when we're trying to get oxygen on Mars, it's no longer the easiest way to get it is out of the soil. So the atmosphere is 95% carbon dioxide. And so that's actually the easiest way that we can access oxygen. And an experiment was just recently landed on the Martian surface with the Perseverance rover, and it was called MOXIE. So that's Mars Oxygen In Situ Resource Utilization Experiment. And that's just a picture of it there where it's housed in the rover. And then you can see it spread apart. There's just a compressor, which pretty much sucks in the atmosphere, compresses it down. And then it's a solid oxide electrolysis cell. So the MOXIE experiment has successfully produced oxygen on the Martian surface already. It produces around 10 grams of oxygen per hour, which is enough for one person to live for about 15 minutes. So it's obviously a very small scale demonstration, but it's a 1 to 200 scale to the larger plant that they're planning to put on the Martian surface in the future. And so yeah, I hope told you a little bit briefly about how we get the oxygen out, and thank you very much.
Thanks so much for that, Beth. That's actually perfectly capping off the entire journey that we've taken tonight. So now we've gone from learning about the history of where these resources come from to how we actually get the resources out of the regolith or the soil on the surface of the moon or Mars or wherever. And now we've actually gone through the processes that we need to actually get the useful end products that we'll be able to use to fuel our journeys to the stars. So I'd like to now bring back the rest of our experts from the presentation so far so that we can go into asking some of the great questions that have been posed by our lovely audience members at home. So without further ado, Meg Bullen asks, this might be a silly question, but is there a way to harvest the static charge as another resource? Would it be worth it? Reuben, I'm looking at you for this question.
Yeah, so there's actually, so there's a method of generating electricity using something called a triboelectric nanogenerator. It's kind of a big word, but effectively you can have two materials that you charge up loads by hitting them against each other, and you can kind of connect the backs of them to electrodes that are connected to each other. And so basically the difference in charge that you generate creates an electric current between them. And you can capture and store that current. So that could potentially be used on the moon. And the vacuum and the excess of charge in the atmosphere might make this easier to do. Might actually make it more efficient. That being said, you don't need kind of existing charge to do that. It's very easy to create the charge difference, so you don't really lose anything by getting rid of the charge. Yeah, good question.
Cool, that's great. No, I think that was answered very, very succinctly. Meg, if you have further follow-up questions, please do post them in the chat. Let's move on to another. Valerio asks, has Brexit affected the UK's participation in any space missions, presumably resource-oriented ones? Does the UK have a space exploration / mining program of its own now? So we can circle around, actually, if everybody that wants to talk about this, because we've got different perspectives here. Abby's in Luxembourg, Beth is in the Netherlands, and Reuben's in the UK. So we can get all sides of the picture.
I think I can jump in. So the key thing with ESA-based missions, like the European Space Agency, is that the European Space Agency is not at all linked to the EU. So Britain is just as much part of a member of ESA as it was before Brexit. So it doesn't impact any of the ESA-based missions.
Yeah, I have just to add to what Beth just said. It's like actually there are several institutions from UK that are participating in the prospect team, that they are developing technologies to analyze the regolith and to analyze the potential for lunar resource utilization of this regolith. And this package is part of ESA, and it's also part of another mission, of a lunar mission. So yeah, they are actually actively participating in several groups from UK.
Yeah, I suppose I'll jump in as well. So there are some cases in which the UK are not kind of included. So for some projects and some funding opportunities through the European Space Agency, they come up with a problem, and they kind of have call for ideas to apply for funding, and often the funding is only available to ideas coming from countries that kind of have bought in. So sometimes the UK doesn't buy into these funding opportunities, but that can be the same for EU countries as well now. I would say. And you say, is there a UK? I can't see the question anymore, but there is a UK space agency as well, with its own funding opportunities for research in this area.
And as far as sort of dedicated sort of space mining funding from the UK Space Agency, as far as I know, there are no major programs going on at the moment. Correct me if I'm wrong, Reuben. But so there is work being done here, but most of it is being funded not necessarily through the space agency itself. At least our work at Imperial is not funded through that route. Cool. All right, maybe we'll move on to another question. Dan Bullen asks, where is all the energy coming from? Nights are long on the moon, right? Does that prevent solar panels from being useful?
Yeah.
Who would like to jump off with this?
I can go. Or if anyone else. Well.
Yeah. Well, I can.
Yeah.
Sorry. You go first.
You go for it. You were talking about the poles in your talk.
Yeah, I mean, it's like depending, I guess that the energy is referring to actually the oxygen extraction that requires some energy from the minerals. And that oxygen extraction actually can happen in many parts of the moon because it's taken from the regolith. And this regolith has oxygen wherever you go on the moon. If you are targeting, if this is a question related with the energy required for the oxygen extraction, it's like, I mean, this lunar nights are 14 days in the equatorial areas. It can have variations depending also the topography. So actually, obviously, also it's true that if you use solar panels to capture that energy, there is not atmosphere. So actually, you can reach high efficiencies of solar panels. So I'm probably Beth will know more about this. I don't know, or you, Reuben. But it's like, I guess that there is a way to capture that energy and process, because also, yeah, I mean, the nights are 14 days, but the days also are 14 days. So actually, we have that balance.
Yeah. Well, also, if say operations are based close to the poles, which is the goal for most of the kind of near-term missions, you find that so the moon kind of rotates on an axis fairly vertically relative to the sun. So that at the poles you get much longer kind of exposure to the sun, similar to if you're in Antarctica in the summer there. You have very long days, sometimes all day. so you can get much more sunlight. In my opinion, I give out to Josh about this loads, that nuclear power should be looked at more. I have a nuclear engineering background before I came to Imperial, so my master's was on looking at nuclear power in space. And that is used. So there are a lot of probes that are sent out into the outer solar system that have little nuclear generators that power them. And NASA is actually designing a more scalable nuclear power system that could be used as well. But it's not really something that ESA is so much researching.
Yeah, for extraction, all of those processes, even though I'm talking about the ones at 900 degrees as low temperature, like of course that's still really, really hot and it requires a lot of energy. And so that's a really important factor. And it plays a lot into how the research is conducted as well. So like, for example, with the hydrogen reduction, so fluidized bed reactor system, there's a researcher in Spain called Thorsten Denk, and he has created a prototype of the system, but it uses a solar concentrator. So it's just a huge kind of mirror system that concentrates all of that energy, and that's what actually heats the reactor rather than an external heating system. And so as well for the research that I'm doing with molten salts, we've put a lot of work in the last year onto like trying to lower the temperature of the process, see if we can still get a reasonable extraction percentage with say 600 or 700 degrees, because even just lowering things down a little bit helps on the energy front and also on materials selection. And then it's also as well important to consider how you can save and store energy overnight. So that's another thing with like molten salts are used on Earth as well for energy storage at solar plants. So perhaps it could be a way of surviving the lunar night.
Cool. That's great. I think that definitely answers the question. It was very thorough responses from all of you that all added to definitely the bigger picture. That was great. Next up, John asks, with the molten salt way of splitting, can the salt be found on the moon or would it need to be taken to the moon? Beth, I guess this is directly to you.
Yeah, so the salt that is most commonly used for this process is calcium chloride. So it's just similar to sodium chloride, which is like table salt. And no, you cannot find that on the lunar surface. But it's a non-consumable item. So you have to, again, the system has to be designed around the idea of zero consumable loss. So you're not replenishing it. You take it once and then you can continually process the regolith. And then, so that introduces a lot of other research questions, like, is there potentially something in lunar regolith that could, get into the salt and lower its efficiency over time that we don't expect when we're using Earth materials as a stand-in? So that's all research that needs to happen.
Great, thanks for that. Peter asks, what do you do to reduce the temperature of the molten salt system?
So the method of doing that is by using different salts. And there's this thing called a eutectic mixture, where if you have two salts that have melting points of, say, 750 or 800 degrees, if you mix them together, the melting point often drops down into a trough. And so there might be an exact composition, say 40% of one salt or 40% of the other, like a sodium chloride, calcium chloride mixture, where the melting point is much lower. Because the key thing that stops you being able to reduce the temperature with a pure single salt is the melting point. Because as you approach the melting point, if you get too close to it, then it gets too viscous and you can't use it as an electrolyte anymore.
Great. That's perfect. All right, Diego asks a question for Reuben. Would the shaking separation method work in low gravity environment?
Yes. So this is actually something we still need to experiment on. But one thing we've noticed is that one of the main kind of problems with it, kind of barriers to scaling, is when you increase the amount of material, you need a lot more force to kind of avoid overpacking the material. So you need to be able to dislodge all of the material to get everything moving and convecting. So in the low gravity, you would expect this to actually work a lot better, because it's much easier to dislodge all the material and avoid kind of trapping your larger particles down the bottom. Yeah, no, good question. Still need to actually prove it, but that's my theory.
There's time. There's time. All right. Chubbs asks, this may sound silly, but could huge amounts of oxygen just be delivered by rockets to the surface? Would that be more efficient? Who would like to take on this?
I can dive in with the. It's always going to be a trade-off, right? So you're going to have to look at the mass of, say, an oxygen production plant or something, the mass of that to land it on the surface, and then the kind of output. And if the output is a lot greater than what you'd have to just land on the surface in this case, then of course it doesn't make sense. But yeah, I think the field of resource utilization and propellant production is definitely going to be changed by the launch mass capability of Starship, because they can just take a lot more to the lunar surface than before. But these technologies are still going to be critical for exploration further afield, and other aspects of resource utilization. It's not just propellant production, but say using the lunar resources to construct landing pads for things to land on the surface and take off again. Like, that's going to be another aspect of space resource utilization that's really important.
Excellent. Yeah. All right. Dale C asks, or says, Starship has been selected as the lunar as a lunar lander and uses methane as fuel. What are the options to produce methane on the moon? Abby, maybe this is good for you.
Well, methane, we cannot find it on the moon. And that is like, actually, if there is other alternative that actually we can find, we will go to use this alternative, that is the hydrogen and the oxygen. Methane can be found in other bodies, in other moons. In Titan, there is plenty of methane there, but on the moon, unfortunately, there is no. It's for one resource that we cannot find there. But yeah, there is this alternative that is using the hydrogen and the oxygen. So yeah, that is mainly the reason.
It's worth noting as well that Starship, Elon Musk's baby, is definitely designed with Mars in mind.
Yeah.
And, the goal, so it's been designed effectively so that they can scrub carbon from the Martian atmosphere and use that to create methane.
Yeah.
I think it's also important to note that the weight ratio of oxygen to methane in Starship, it actually is 78% of it is oxygen, and that's why there's always such a heavy focus on like where we can get oxygen from in space, because it is always the largest mass component.
Mm-hmm.
Sure. Oh, that's excellent. Thank you. I think we have another question. Yeah. Oh, make us a follow-up. Are there particular benefits for hydrogen reduction despite it having relatively low yield and requiring hydrogen already being used as a fuel source? I.e., why has NASA looked so much into this?
So I think it's in terms of like why they've looked into it historically, it's just one of like the first processes that was discussed, one of the first processes demonstrated, and generally a solid gas interaction is a much simpler interaction to deal with than dealing with molten species. And so so if you're comparing like the history of the process as well, fluidized bed reactors are really commonly used in many industries already on Earth. And like, for example, the molten salt electrolysis process that I work with, the FFC Cambridge process, it was only invented in the year 2000. And then in the 20 years since then, it's been commercialized slowly over that time, and so it's a much newer process, and so there's just not as much history there.
Great, thanks. Meg also asks, sorry, have there been discussions about the potential downfalls of privatization of such resource harvesting, rather than using lunar resources in the pursuit of knowledge and they're used commercially? I know, Abby, you have some strong feelings about this. Would you like to kick things off?
Well, I mean, there are some discussions, and actually right now we are at a point that there are like two different orientations. I mean, everybody agrees in one thing. It's like we have to go to the moon and we have to use the resources that are there. Then it's like we have several interpretations of the policy of the main, the Outer Space Treaty, that is like the international agreement that 101 countries sign and ratify, that at some point says that nobody can get the moon appropriation from national appropriation, let's say. And then from then there are countries that have some interpretation of that, like for example, United States, Luxembourg, Japan, that they have the interpretation like, okay, if a company goes there and take the resource, actually is not national appropriation. So the resource the source is part of the company. I mean, the company owns the resource. This is more or less like if you are in the ocean, far in the ocean, and you capture some fish. So you are the owner of the fish, but you are not owner of the ocean. And then there is the other part that they are more for another treaty that it's called the Lunar Treaty, that what it says is like actually the resources have to be used for the benefits of all the humanity. So it's like, okay, if these resources are used for the benefit of the humanity, still companies can go to the moon and can do the resource extraction and utilization. But there will be an implementation of international bodies, like some kind of a United Nations type of body that regulates that, and probably also the companies will have to pay a tax for using this money that they receive, a part of this money that they receive, to do something for other countries that are not that develop in the technology or whatever, or the space. So this moon treaty kind of thing is more supported by other countries like China or Russia. Also, there are other countries like, I would say, France or Germany, that they are like not still going to any directions. So it's like that is the point that we are now. We are in this vision, like one side that is like just go there, take the resources. The companies take the risk to go there and take the resources, so they have all the right to have all the benefit of that. Or the other part is like, yeah, the resources of the moon have to be used for the benefit of the humanity. So you have to go there. But if the money that you get have to be used, part of it, like a tax, for the benefit of other countries. So that is where we are now.
Yeah, very clearly it's not a clear, a clear topic to sort of prize apart. And there's so many different facets. Yeah. I mean, it's like, who owns the moon? Who owns the resources? Who has the right to do these things? Who decides who has the right to do these things? There are a lot of very large and very open questions that, I think the research community, but also the policymakers need to start thinking about. And it's definitely a tricky topic with a lot of work to be done yet. I think we have time for probably one more question before we have to start wrapping things up. Diego asks, besides the obvious benefits that these research would bring for space exploration, could any of this be applied to Earth? Reuben, I guess this is Reuben and Vestos, actually, yeah. So
yeah. I'll start with the extraction technology side of it. These processes are all derived from processes that are already used terrestrially, often in the metallurgy industry. So that's what molten salt electrolysis is normally used for, the production of metals and alloys. And I think when you're doing any research into how to translate these technologies to space, there's always going to be huge benefits for that. So you're looking into how to automate things, how to make things more efficient, how to recycle consumables so you're not wasting things. And all of that's brilliant for the terrestrial industry. And a really big one for the electrolysis processes is to produce oxygen directly, we need to identify an inert anode material. So an electrode where the oxygen is generated directly and comes off the anode rather than reacting with it. So terrestrially at the moment, carbon is what's used in the FFC Cambridge process or in the aluminium industry, which is also a molten salt electrolysis process. And that generates huge amounts of carbon dioxide and carbon monoxide. And so any research into how we can produce oxygen directly on the moon could then be fed back into the terrestrial research field of how we can make these processes more sustainable.
Awesome.
Yeah, I suppose, yeah, I'll add in a quick add on to that. I suppose, Diego, you definitely know, but the mining industry is also very, very water intensive, the mineral processing side. So I suppose any research we can do into dry mineral processing from the moon that might have applications back on Earth, at least somewhat add to the greening of the industry. Like it is used a small bit on Earth, and there's also a lot of applications for electrostatic separation in other industries like recycling, for separating out different materials, and recycling plants can really help with that. And of course, like Beth said, kind of really the aim of the game with all of this research is to reduce waste, have sustainable closed system loops. And so the more waste we can reduce in Earth applications of any kind, really, I think there's no real denying the benefits that brings.
For sure. Abby, do you have anything to add? No?
No, I think fine.
Okay,
I think they cover everything.
Perfect. Great. Well, we're almost out of time, unfortunately. Thank you all in the audience so much for the questions that you've contributed. It's been a huge help, and it's really facilitated such a great discussion with all of our panel of experts here. So I'd like to just thank you all so much for participating in the evening tonight. And I look forward to hearing more of your thoughts. And if you'd like to continue this conversation on Twitter, please do so. But remember, please use the hashtag Pint21. I'd like to thank for one last time our speakers, Abby, Reuben, and Beth, for their excellent presentations and for sharing all of their knowledge and expertise with us over the past hour. Thank you again so much. And yeah, last but not least, Pint of Science is a part of a week-long, or this event is part of a week-long Pint of Science series on a variety of different topics. So if you liked this broadcast, there are many more that are happening throughout this week. Please do check out our website at www.pintofscience.co.uk for a list of all of the different shows that are being broadcast over the course of the next few days. Thank you so much again for participating. Cheers and have a good evening.